You know the scene, right? The giant hole in the road, traffic backed up for miles, just chaos. And it's all because of a broken pipe. But what if I told you we could fix that pipe from the inside, using some pretty incredible material science and avoiding all that disruption? Well, today, that's exactly what we're going to dig into, the science of fixing things we can't even see. So this is the entire ballgame. You've got a critical pipe. Maybe it's buried deep under a busy street. You can't see it. You can't touch it. So how on earth do you fix it? The answer, it turns out, is absolutely brilliant. It's all about building something brand new in a place that seems impossible to get to. So let's start with the problem itself, because beneath our feet, there's this massive, hidden network of pipes that we all completely depend on. And most of the time, it's out of sight, out of mind. But when one of them fails, well, that hidden problem suddenly becomes a very, very visible and disruptive mess for everyone. Oh, we have all been stuck in this exact traffic jam. You see the giant excavator, you hear the noise, you're stuck in detours, and it's all for one little broken pipe. This is the old school brute force way of doing things. It's slow, it's super expensive, and honestly, it's just a massive headache. You gotta think, there has to be a smarter way. And of course there is. The modern solution is just, it's so clever. Instead of digging everything up and replacing that old broken pipe, engineers have figured out how to build a brand new, super strong pipe directly inside of the old one. The process itself is pretty fascinating. You take this flexible liner that's been soaked in a special resin, and you insert it right into the damaged part of the old pipe. Then it gets inflated and cured right there, in place. And just like that, it forms a brand new, rock-solid pipe inside the old one. So what in the world is this high-tech liner actually made of? To really get how this works, we have to look at the ingredients in the recipe. This new pipe isn't just one material. It's what we call a composite. That just means it's a team of different materials working together to be way, way stronger than any of them could ever be on their own. Okay, the absolute best way to think about this stuff is to imagine reinforced concrete. You've got two main players. First, there's the resin. That's your concrete. It's the liquid glue that soaks into everything and then hardens up to fill all the gaps. And then you have the fibre. That's your steel rebar. It's the skeleton that provides all the real structural strength. So let's zoom in on that glue for a second. The system uses these special two-component silicate resins. Look, that's just a fancy way of saying it's like a high-performance epoxy you might get at the hardware store. Two parts are mixed together, and that kicks off a chemical reaction that makes it incredibly hard and durable. These different types you see here, they're probably just tweaked for different conditions, like if it's cold or wet underground. But the mission is always the same: soak that fiber and harden into a single, seamless, corrosion-proof shell. And here's the rebar, the skeleton. This isn't just some random fabric. It's a specially designed fiberglass mat, engineered to soak up that resin perfectly. You can see there are two main weights, a lighter one and a heavier one. But check out that fiber content. In the finished, cured pipe, more than half of its total weight is pure fiberglass. That, right there, is where all the incredible strength is coming from. Okay, so we've got our recipe of resin and fiber. It sounds strong, but what does that really mean out there in the real world? How does this stuff actually perform when it's under pressure? Well, let's look at the actual data that proves just how tough this new pipe really is. All right, our first key number is something called the Modulus of Elasticity. It sounds really complicated, I know, but the idea is actually super simple. It's just a measure of stiffness. Imagine you're trying to bend a cheap plastic ruler versus a thick steel one. That steel ruler has a much higher modulus of elasticity. It just really resists bending. And would you look at these numbers, they are huge. We're talking thousands of newtons of force for every single square millimeter. What that number really means is that this new pipe is incredibly stiff. It's stubborn. And that stiffness is exactly what allows it to hold its perfect circular shape and not get crushed by tons of soil, groundwater, and traffic rumbling overhead. It just refuses to deform. Okay. So our second key number is flexural strength. Now, if stiffness was all about resisting bending, strength is all about resisting breaking. Let's go back to our ruler. This is the measure of how far you could bend that ruler before it gives up and finally snaps in two. And again, these numbers are seriously impressive. This tells you exactly how much force it takes to actually break the material. This immense toughness is what guarantees that the new pipe can handle everything the world is going to throw at it. Shifting soil, vibrations from trucks, high water pressure, all of it, without cracking. And this chart just shows it perfectly. It's plain as day. When you use that heavier fiberglass mat, you get a clear, measurable jump in braking strength. And this isn't just numbers on a page. It's a choice. It lets engineers pick exactly the right amount of muscle for whatever the specific job needs. All right, so we've geeked out on the recipe, we've looked at the performance data, but let's bring it all back. What does all this chemistry and physics actually mean for that broken pipe under the road? Let's put it all together. It really all comes down to this. The high stiffness stops the pipe from being crushed, and the high strength stops it from cracking. Those two properties work in perfect harmony to create a repair that isn't just some temporary patch. It's a brand new structural pipe that is literally built to last for decades. It's just amazing. It shows that sometimes the most elegant solutions to our biggest problems are happening right under our feet, powered by incredible science that we never even get to see. And it kind of makes you wonder, right? What other invisible engineering is out there, quietly protecting our world every single day? Thanks so much for joining me.